All right. This chapter is not really about database management systems. It is rather more related to operating systems. Since we are offering operating systems and database systems courses in the same semester, same year, usually, less than half of the students have taken operating systems classes. So let me give you some, let me go over some, how should I say, background about this storage design, storage systems. And this knowledge is needed to understand why DBMSs are designed in that way. So in computer architecture, we have storage devices like SSD, hard disk drive, and these hard disk drives are usually connected to SATA interface in the old days. But then SSD, the flash-based electronic storage devices came out, and they are now connected to PCI interface. And PCI interface is used to connect those peripheral devices like network card, GPU, and other external devices. And storage devices connected to this PCI interface will transmit data to DRAM using PCI interconnect. And the size of the data transmitted between storage device and DRAM is usually 4 kilobyte, and we call that a page, 4 kilobyte page. And when CPU executes load instruction or store instruction or move instruction, then the data that resides in main memory will be copied to CPU cache. And in CPU cache, we have multiple levels: last level cache, L2 cache, L1 cache, and the data granularity that are transmitted between DRAM and CPU cache is 64-byte cache line. So when CPU performs some instruction, it needs to bring cache line from main memory. So it will it will store the data in the CPU cache, and then eventually it will copy the data from the cache line to registers. And only after we load the data in registers, we can apply some arithmetic instructions like add, multiply, and so on. And when a new cache line is requested by CPU, it will first look up its CPU cache, and if it doesn't find it from the cache miss occurs, and the cache line, one of the oldest cache line will be evicted from the cache, and the requested cache line will be copied from DRAM to this CPU cache. And to read the data from disks, we are not calling those machine instructions, but instead we call a system call. Read-write, those file system calls are called. And operating system is responsible for bringing up those 4 kilobyte pages from disks to main memory. And once we, once we bring a large 4 kilobyte page into main memory, then afterwards, those data will be managed in the granularity of 64-byte cache lines. And in old days, when I was an elementary school student, I used to use this tape drive to play games. So I had this very old computer, and to play a game, I had to plug. I had to put this cassette tape drive into this mechanical device and play. Click the play button, and I had to wait for like 30 minutes. Yeah. So it is because this tape drive has this plastic thin tape coated with this magnetic, magnetic materials, and this this thin tape drive could contain very small amount of bytes, and usually a game, using this single tape drive, we could store just one single game, and there is this tape, how should I say? There is this sensor device called tape head, and this tape head to scan all strips. All, how should I say? This is called a strip. So it has to scan all the bytes from this strip. So unless we rotate this wheel entirely, the program is not loaded into the main memory, so I couldn't play any game. But then a better storage device came out, which we call floppy disks. And these floppy disks work in two-dimensional way. So this tape drive works in just one-dimensional way. We need to rotate this reel, and we need to wind all these tape drives. That is one-dimensional movement, but these floppy disks work in two-dimensional space. So we have this very thin plastic disc inside this cover, and that plastic disc is rotated. And while this plastic disc is rotated, there is a sensor device that moves back and forth and scans those bytes from this small slit, small hole. So it supported two-dimensional movement of sensor devices. So in that, because of that, it worked faster. And oops. Okay. So anyway, but still it was slow. And then this hard disk drive was developed, and I uploaded this short YouTube video in iCampus. So maybe it'll be better for you to watch it instead. Where is it? So if you're interested in this tape drive, you should watch this video. If you're interested in hard disk drive, then maybe you should watch this video.
Imagine every picture you took over the past year, all saved within the area of a single dot of ink from a ballpoint pen. Well, this is approximately how compact data is stored inside a hard disk drive. And in this video, we're going to open one up and see how an entire library worth of books is able to fit within the surface of this metal disk. We'll start by opening up this hard drive and detailing the components inside. After that, we'll dive into exactly how the drive stores data using the read and write head, and in the process, we'll look at the tracks, sectors, and magnetic domains of the metal disk. Finally, we'll explore some of the latest advances that enable over a terabit of data to fit within every square inch of the disk. This video is sponsored by PCBWay. More on them later, but for now, let's jump right in. On the inside of this drive, we find a variety of components. Here's the disk, or platter, that stores all the data, and depending on the storage capacity of the drive, might be multiple platters tall. The disk is composed of an aluminum-magnesium alloy with multiple coatings of other alloys, but the magnetic functional layer is this 120 nanometer thin layer of a cobalt-chromium-tantalum alloy, which has small magnetic domains or regions whose direction can be manipulated via external magnetic fields. The platter is mounted on a spindle which spins at a speed of 7,200 RPM, using a brushless DC motor at its center. Next, there's a head stack assembly, with one arm above and one arm below each disk, and with a slider and a read-write head at the end of each arm. The slider is uniquely designed such that it catches the airflow generated by the ludicrously fast-spinning disk and uses the airflow to float or fly the read-write head so that it's only 15 nanometers or about 100 atoms away from the surface of the disk. For reference, here's the thickness of a sheet of aluminum foil. Because the ARM assembly flies on top of the spinning disk, it's only brought over the surface when it's at full speed. And when the disk is not spinning, the ARM assembly is parked to the side on a small piece of plastic. Back here, a voice coil motor composed of a coil of wire and 2 strong neodymium magnets above and below is used to move the entire
I think
ARM
this is more
stack.
than enough for you guys to learn about hard disk drive. So let's go back to our lecture slide. So hard disk drive works in also 2-dimensional way. So this disk arm moves back and forth. At the same time, this disk platter rotates. So database systems were designed considering the characteristics of this hard disk drive. How should I say? So in the following lecture, we are going to consider disk seek time and access time. No, we are going to consider disk seek time and data transfer time. So access time is the time it takes from when database systems request a specific data to when the data is actually delivered to the application process. And this access time consists of 2 times. One is the seek time and the other is rotational delay. Rotational latency is the time when we when we rotate the disk platter. And seek time is how long it takes to position disk arm over a correct track. And this rotational delay depends on the rotation speed. The high-end disks support this rotation RPM, 15,000, but usually we support 7,200 RPM. What should I say? So suppose we have this disk platter, and suppose we stored a large table sequentially. Then let's suppose we have disk arm right here, and we started writing a disk page. After we write a single disk page, the disk platter will rotate slightly. So it's going to move this way, and the second disk page will be written, and then it will rotate again, and the next page will be written. We call this a track. If all disk pages are located on the same track, then we can avoid the disk seek operation. And if you have a really large table, the table will span across multiple tracks. So suppose we stored a single large table on 3 different tracks. And if we access each page sequentially, then we need to we need to move disk arm only 3 times for the outermost track, and then middle track, and then innermost track. But if we access that large table in a random fashion, then we need to rotate this. We need to rotate this platter and also move disk arm. And then for the next disk page, which is located far from the first page, we need to rotate disk platter and then move disk arm again and again repeatedly. So random access was much slower than sequential access pattern. So when we talk about these performance issues of database management systems, you need to consider disk seek time and data transfer rate. And data transfer rate or rotational delay, I guess they are similar. You do need to clearly distinguish these metrics. But key message you should take from here is that random access was much slower than sequential access. I don't recall the exact number, but usually to read 4 kilobyte disk pages from random position, maybe I should check it. Give me 1 second. Reading 1 megabyte file sequentially is only 4 times slower than reading random 4 kilobyte disk page. Is it memory? Just too small. So, where is it? Reading 4 kilobyte disk page randomly from SSD takes like 150 microseconds, and it's not just 4 times. It is from memory. Reading 1 megabyte sequentially from main memory takes about twice longer. And reading 1 megabyte sequentially from disks take like, how long? 6 times? 6 times slower than reading just 4 kilobyte memory, 4 kilobyte disk page from the SSD. So sequential access is much faster. That's the key message that you should take from the previous slide. So here it says that sequential access pattern does not need disk seek operation except the first page. But when you access table in a random order, every access required disk seek operation. And then, nowadays, SSDs are very commonly used in many systems. And also, I uploaded an interesting video that introduces how SSDs work in iCampus. So I recommend you should watch it. This USB drive SSD, they use the same technology. And if you watch that video, it's going to introduce, you will find out why we care about block. What is block? Block is a set of contiguous, consecutive pages. In a single block, we have large number of pages, 4 kilobyte pages, and once you initialize a block, you can start writing some data in each page. But once you write a data in a page, the page cannot be updated. The page cannot be updated until the entire block is erased. Okay. So this is what happens. Suppose we stored 4 pages contiguously, and then this first block is now full, and suppose an application wanted to update this page number 10. Then instead of overriding this page number 10, SSD will place that page number 10 in a different block, because there is no free space in this block, and this page is immutable once it is written. So we will mark this first page as a garbage and write a new page, write the page number 10 in a new block. Similarly, if another page 12 is updated, we write it in another block where we have free spaces, and then mark the old page number 12 as a garbage. So what this means is the actual location can change it depending on whether the pages have been updated or not. So SSD need to manage a mapping table to keep track of those physical location of each pages. So they manage local page address and physical page address. So initially, when page number 10, 11 they are written, then inside the SSD we will have this mapping table. It says that logical page 10 is located in number 1, physical block number 1, and 12 is written in physical page number 2, and so on. And later, when page 10 and 11 are updated, 10 and 12 are updated, their physical block addresses will be changed. And we call this flash translation layer, FTL. Flash translation layer or flash translation table. FTL is a more commonly used term. And these flash devices are electronic chip, and it has some limitation. You should watch the video, but basically the problem is that once a block is full of garbage pages, then SSD will erase this entire block so that subsequent write operations can use these free spaces. This is called the erase operation, and there is a limit in the number of erase operations that can be performed per block. So if we erase this particular block like a million times, then this block will become unusable. That is called wearing issue. So to avoid this wearing issue, SSD needs to balance these page locations so that a particular, single block is not worn out too much by write-intensive application. All right, that's it. That was brief introduction to storage devices, and the only key message that you should remember is that sequential operation, sequential disk access or SSD access is much faster than random access. SSD is electronic device, but still its random I/O performance is slower than sequential I/O performance. But I guess that is out of scope of this database systems course. So still, even if we use SSD, still random access is slower than sequential access. Anyway, so let's move on to the next chapter, which introduces how DBMS stores tables in a file. So usually, a single database table is stored as a single file. We may use native Linux file system, or some commercial DBMS like Oracle doesn't use file system, but instead it may write tables directly onto the raw storage devices without using file system. But anyway, so usually we store each table in a file, and each file is just a sequence of records, sequence of student records or instructor records and so on. And a record is a sequence of attributes, as you guys know. And to simplify our discussion, to avoid confusion, let's just assume that we have very small records that can fit within a disk block, disk page. And for now, we will assume all attributes are of fixed size. So varchar type will be considered later. Varchar type is for variable length string. We are not going to talk about it for now. So when we have a fixed sized attribute, then it is easy to manage these records in storage devices. So suppose instructor ID is of 4 bytes, name require 10 bytes, department name 10 bytes, and so on. Then how can he read the 7th record's name? How can he find the location of this guy? It's easy. We do simple calculation. Total, we have how many? 28 bytes for each record. So if you add these numbers, you will get 28. So every record will use 28 bytes. So for this 7th record, we need to just multiply 6 by 28. And then, since the name of the instructor is the second attribute, we need to add the size of the first record, which is 4 bytes. Then we can locate the offset of this specific attribute value and ask a file system to read the data from disks. But what if we delete a record from this file format? We executed delete from statement. That delete query will delete one of the records in the table. What should we do? We need to shift every record by 1 position. Oh, this is bad, right? It has to touch too many records. If we delete the first record, then all the rest of the records should be shifted. This is going to incur too many disk IOs, and it will perform really poorly. So, I have an animation here. So L side will be moved up, gold will be moved up, cut will be moved up, California will be moved up, Sing Creek will be moved up like this. That's bad. So instead, a better option is to just move the last record to fill up that deleted record. Every record has the same size. Every record is of the same size. So instead of shifting these records, we can simply copy Crick to replace Einstein, and then reduce the size of the file to eliminate Crick. Then we are done. So database systems are based on set theory, so we don't care about ordering. It is okay to move around these records. And there's another option. Do we really need to fill up those empty spaces? Maybe not. If all records are of the same size, then instead of filling up this empty space, we can just keep a linked list to keep track of those free spaces. Suppose record 1 has been deleted, 4 has been deleted, and 6 has been deleted. Then using some metadata, we can keep track of these empty spaces so that subsequent insert operations can use these free spaces. Right. That was for fixed sized record, and for variable length record, how can you manage those attributes? Suppose we have this table, ID, name, department name, salary. Except the salary column, the last column, the first 3 columns are of variable length string type. So what do? We need to keep track of the starting offset of these 3 variable, actually the last one as well. No? Oh, no, we don't need to do that. So for these 3 variable length attributes, we reserved 4 bytes, these 4 bytes will, each 4 bytes will keep track of the starting position of these records and also the length of the record. So if the first attribute uses how many? 5 bytes. Oops. Give me 1 second. Okay. So if this first record uses 5 bytes, then we will store the length in this first 4 byte, and also its starting offset will be stored here. And for the second attribute, its starting offset is 26. We will store it here, and its length will be stored here. And for the third one, we do the same. And for this last fixed sized record, we don't need this metadata. Instead, we will store just the value in the next 4 bytes. And then we use another byte to keep to find out whether attributes have null values or not. So this 0, 0, 0, these 4 bits indicate that none of these attributes are null. If you store null value in department name column, then you will not need this third metadata. Instead, you will set the third bit of this bitmap to 1 to indicate that the third attribute has null value. Right? So that is how we manage variable length records in a table. And how do we manage a table with lots of variable length records? So variable length records are those records with variable length attributes. So if a record has a variable length attribute, its size will be also variable. Therefore, the whole record size will not be fixed. And a table needs to keep track of the location of those variable length records. So how do we do that? There's a solution called the slotted page. And basic idea of this slotted page is similar to what you just saw in the previous slide. We use metadata that keeps track of the starting position of each record. So slotted page manages the number of records and free space location, the position of free space, and location and size of each record. This is an array. We keep an array of each record location and size. So it will be easier to explain this using an example. So let's look at this. Suppose we are storing 3 records, and they have primary keys, numeric primary keys, 30, 50, and 40. And let's assume that it doesn't have to, but let's assume that we want to store these records in sorted order of primary keys. So 30 needs to come first, 50 should come last. So the logical view is shown right here. In this slotted page structure, we have metadata. In this metadata, we keep track of how many records are stored in the current page. So let's insert number 30. Initially, it will say the number of records is 0. Then we can store this first record at the end of the page, and then increase this number to 1. And then, since the length of this record can be varying, can be different per record, we should keep track of the starting offset. So let's assume this last record occupied 48 bytes, then its starting offset will be 4000, and that 4000 will be stored in this array. And although I didn't write it here, its length should be also written in this array. 4000, 48 should come here. And then let's insert the next record 50, midkey 50. In the previous slide, I mean, so yeah, after writing this first record, we need to update another metadata which is not shown in my example. There should be a pointer that points to the end of the free space. So when we insert the second record, using the free space pointer, we calculate how many bytes, we compute what will be the starting offset of this second record. So initially, the free space pointer will have 4000 as its value, and if this second record requires 100 bytes, then we deduct that 100 from that free space pointer, and then update the free space pointer.
Why can we use just the last record in the array as a reference to the free integers?
It is because some records can be dynamically deleted in the middle.
Okay,
Well, yeah, yeah.
So we need the last record in reference to the edge of this free space.
And there is no single perfect solution. Depending on how you implement this, design can be changed. Okay. This is not the only solution. There can be many variations. And when you don't care about the ordering, then the design can be simplified. So we store key 50 in the next position here in the free space, and then we append another offset information into the array, and then increase the number of records counter. And then let's insert another one, key 40. Then using again the free space pointer, we figure where this third record should be stored, and then we need to update this offset array based on the sorted order of these primary keys. If we don't care about sorted order, then it doesn't matter. But if we care about sorted order, then this record offset array should be somehow, elements from this offset array should be shifted to make space for this new record. So it says that the record positioned at 4000 has the smallest key, and the key positioned at 3850 has the second smallest key, and so on. Okay. So without shifting, without touching previous records, we can keep the sorted order within this page. And if if more data are inserted, and if this single page is not sufficient for those additional data, then of course we need to allocate another page and then do the same job. So any question about slotted page?
In the scheme that you just explained, what happens if we update some record in bigger value? Then we just use free space and delete.
Yeah. Also, there is no fixed solution to that problem. Let's say currently this second record occupies 100 bytes, but somehow we stored a larger string value in the maybe instructor's name column, and this size will this size will be expanded. In that case, we need to shift some records. So it is like creating the whole new page format from scratch. Or alternatively, you can just put a deletion mark for this record and put that new record in the free space. There is no fixed single solution. I'm just giving you some one of the representative design of managing variable length records in database systems. Okay.
Where exactly is the pointer stored? Is it stored next to the number of records, or?
That also depends on your implementation, but yeah, it can be positioned at the beginning of the page or it can be positioned in the middle. It doesn't matter actually. And in this figure, we have a fixed, we should have some fixed number of metadata in the beginning. We have some fixed number of metadata in the beginning, and then since this array can grow or shrink, we put it in, we put this after the fixed sized metadata. All right, can you move on? Question?
Then if we set the recorded offset position, then why in metadata there is a data that will present the first?
You mean why do we need the free space pointer? Well, I don't get the point of the question.
메타데이터에서 이 3,850을 그냥 처음으로 가리키는 게 있다고 하셨잖아요. 근데 레코드 오프셋 이걸 가지고 있는데 그 처음을 가리키는 게 왜 필요한 거죠?
Okay, so the question is, so I told you that there is usually, not always, but there is usually a pointer that points to the beginning of, or the end of the free space, right? So it should have 3850. And his question is, why do we need to keep this duplicate metadata? Maybe we can eliminate this metadata, yeah, but if we do not have this separate free space pointer, then you need to scan this entire offset array to find out the minimum. Okay? Yeah? Is it okay? Can I move on? All right. So we just learned how to manage variable length attribute, variable length record, variable length, page for variable length record. And then let's see some file format. We will first learn very simple file format called heap. And then we will move on to sequential file format and then B3 and hash. This heap is not the data structure heap. In data structure class, you guys learned max heap, min heap, right? Min max heap. This heap is not that indexing structure. What this means is just bunch of randomly accumulated data. That's what this heap means. So suppose we have a table with 4 records. And let's assume we inserted this Srinivasan first into the table and Singh as the second record. So we inserted these records in this particular sorted order, in this order from up to bottom. Then we will simply place this first record, second record, and third record in the first page. And for the first record, since this first page is 4, we move on to the second page and store it there. And then let's assume application deleted Calipari. Then we will update the slotted page structure to remove it from the page, corresponding page. Okay? We do not move around. We do not shift this last record. And later, when another record is stored, we store it in the free page, free space of the first page. And when another record is stored, we place it at the end of the file. And if the first record is deleted, we just remove it from the first page. This is how we manage heap file format. So we don't care about ordering. These records are not stored in the insertion order, and these records are not sorted by their primary keys. They are just completely random. So some records, I mean, even if we inserted these records in this order, they can be placed in different order in a file. That is a heap file. So how do we manage free space in a large heap file? The answer is we use mapping called free space map. So suppose seven. Okay. So suppose we are using 3 bits as a free space map for each page. Then how many numbers can we represent using 3 bits? 7, right? 7. So 0, 0, 0, 0, 0, 1, 1, 1, 1. This is 7. So we have a total 8 distinguishable numbers, but we take this maximum number from this 3 bit and partition a single disk page into 7 subspaces, and then give me 1 second. And what this number actually means is how many subspaces are free to use. So when this 3 bits indicate 100, I mean this is number 4 in decimal number. So it means in this first page we have 4 free subspaces, completely free spaces. And 0, 1, 1 indicates that the second page has 3 completely free subspaces. That's what it means. And we are gonna manage an array of these we are going to manage an array of these bits, but if you have too many disk pages for a single file, then we should build a hierarchy. So suppose this is the given array of that bit encoding, and now we use max heap and group these 3 bits, 3 numbers, and then choose the largest one, and group these 3 numbers and choose the largest one, and group these 3 and choose the largest one. So what do we do with this hierarchical free space map? What do we do? Suppose an application DBMS wants to store a very large record. So if that record requires, how should I say, more than 5 subspaces in a single disk page, then we'll look up this upper level numbers and then find, let's just assume that a single record requires these large spaces. large subspaces. Then we look at these three numbers, and then we find out that maybe the first group can be used for this new record, while second group can be used for this new large record, but third group cannot cannot be used for this large record because underneath this the maximum free subspace is only 5, so which is smaller than the requirement. So let's not go there. That's how we use this hierarchical free space map. So among these two, it is up to you. You can go to this first child or second child. I mean, after visiting the next level, again we look up these numbers and then find any disk page that has sufficiently large free spaces for the new record. And let's assume that we selected this one. And we needed 6 contiguous free spaces. Unfortunately, this disk page has fragmented. Disk 3, page 3 is fragmented. So we have this some data in the middle. Then we do defragmentation. So we need to shift this used space to the end or to the beginning, and then make 6 contiguous free subspaces and store the large data in the contiguous subspace. Question about the heap file? No?
heap file is something that we don't need to record in single page, but in this case we move it to another page and this is significant because we don't move the
So here, this slotted page structure is for disks. And if possible, it is better not to move around these records. But if needed, it is okay. It is allowed to move around these records. So once you load this disk page into main memory, the file format will be preserved, and some query thread may access this last data with key 30, and another query Q prime may access the the record with key 40. If these two threads are currently accessing these two data items, then it is not allowed to move around these data. They are protected, but when there is no queries that are currently accessing any records of this table, this page, then it is okay. To make a free spaces, you can move some records to the right or to the left, and then store new large record, and then dump that updated page to disks using F-Sync system call. Then the whole page will be atomically written to disks. Okay? And that question is somehow related to the concurrency control that we are going to talk later. So maybe at this point, maybe you just need to know that it is desirable not to move around the records within the page, but if needed, we have to move those records to make some large free spaces. Okay, and let's move on to the next file format called the sequential file. This sequential file format is used for applications that perform sequential write and sequential read. And a good example is RocksDB, which is commonly used key value store in cloud systems. And unlike a heap file, this is sequential file sorts data. They sort data according to some key. In this example, instructor's ID column is used to sort out these keys. Those records. These records are sorted by ID of the instructor. And so in one of the previous slides, I introduced there are 3 options. But now we have a requirement. These records must be sorted by ID column. Therefore, we cannot use this free space. We cannot replace this deleted record using the last record. That is going to mess up this sorted order. So we cannot move string to this first position. This is not allowed. So another option is to move all records by one position. As you guys know, this is too expensive, so we don't do that. Instead, we use a pointer, free list pointer. So to keep the sorted order, every record has additional metadata that points to the next record in the sorted order. And if another benefit of managing this pointer is that the actual physical location of these records don't have to follow the sorted order. Since we have these pointers, when a new record is inserted, the free space can be used for the new incoming record. But this is not good. If possible, these records must be stored in a sorted order to avoid random accesses. The main reason why we use this sequential file format is because disks are fast for sequential access. So if possible, they should be sorted. But just to utilize some disk spaces, we may store new records in those free spaces and connect these records in sorted order using pointer metadata. But if we do that, that is going to hurt I/O performance. So to restore sequential order periodically, we need to reorganize the entire file to eliminate. We need to reorganize the entire record to maintain the sorted order to match the physical and logical order the same. We should reorganize them. And question?
Regarding the sequential access type, right? File organization. So it means that if we try to randomly access the data that is no longer ordered sequentially, right? And how does the system know whether the new tuple that was inserted is actually ordered correctly?
Maybe I didn't get your question.
In one of the slides, so when we insert new data, right? Even though it is inserted like in the middle, right? 76766. Next.
Previous one?
No, next one. Yes, this one. So we insert this value, right? And it is not ordered, right? And if we try to access this value, right?
Correct.
So how do we know that whether this value is ordered or not? Because how do we access it in the first place if it is stored in a certain address, right?
This is a linked list.
But
So
how linked list can be random access?
you think this is? So we use a linked list. So to access the first record of this table, we start from this record, and then for the next record, we follow this linked list, next pointer, and access this, and access this. Then eventually, we'll access creep as the last record. Okay?
So does it even depend on the order? Because in the English we need to traverse all the blocks up to find the result, right? So it does not depend on order.
Depends on what? I'm sorry.
It's not sorted, right? Even if it is sorted or not sorted, to find a value inside that we need to traverse all the other blocks. So it doesn't depend on the order.
Ah. So you mean, so her question is very interesting. So what if we want to read a record with a specific ID? Then we need to scan the entire table anyway. And that's the question. What do you think? We do binary search here. So we just pick median record, and let's suppose we found this, and what is our search? Let's just suppose we are looking for ID 45565, yeah? And we just pick this median, and since this is greater than this, we should pick another median from this second half group, and then if it is smaller or greater, then we do this binary search repeatedly until we find it. But while we are doing this, we should also consider this next pointer simultaneously because the actual order of this table may not be perfectly match the sorted order. So that is going to make some problems. That is why we need to periodically restore the ordering. Any other question?
In sequential file, we access each record sequentially. In heap file, we can't access it sequentially.
I'm sorry?
In heap file, we can't access it sequentially.
In heap file, can you access record sequentially? What do you mean by that? I'm not feeling really good today. I'm sorry. I slept very late last night, and I had to wake up very early. So anyway, so I'm sorry. Can you repeat the question?
In sequential file,
Sequential file.
we access each record with sequential order.
Uh-huh.
But in heap file, we can't access it as sequential order. Then what should be? How we?
So I don't still get your point. So you mean? Can you explain? Can you ask the question in Korean? I will translate it.
세케이션 파일에서는 이렇게 링크들이 있으니까 처음부터 이렇게 시킨적하게 셋했잖아요. 이 파일에서 저희가 페이지별로 저장을 하잖아요. 페이지 단위에서
No, it is completely random. P file is just random file format. There is no guarantee about the ordering of the.
이 파일은 오더링이 없잖아요. 그러면 시킨적 파일에서 비스킨을 찾을 수 있는데 이 파일에서 그렇게 찾을 수가 없는 거잖아요. 그럼 이 파일에서 랜덤으로 찾는 거예요.
No. We have to scan everything from beginning to the end. So his question is, how do we find keys when a table is stored in a heap file? So in heap file, there's no order. There's no order. So we don't even scan these records in this logical order, but we just scan everything in physical order. You need to do the brute force scan to find, to locate a specific record. And actually, I have some more slides that analyze those search and insertion costs in the following lecture slides. So we are going to talk about it more in detail. Okay. Question?
네, 그 리올거나이즈 한다는 게 식타임을 줄이기 위해서 시간이 지남에 따라 그걸 다시 컴팩트하고
So without reorganization, we cannot do the binary search. That is main reason. Maybe we can do that, but that algorithm is going to be very complicated.
So databases, like, they track whether the newly inserted data, whether the table is dirty or not.
So how do they keep track of whether page is updated or not? I think we need to wait for 1 month.
Because I believe,
So-
since right now we're like covering the material on a very high level, on very abstraction, I have a lot of questions whether like how those intrinsic mechanisms like search, insertion, fast search is supposed to work.
Sorry, you don't have to wait for a month.
I feel kind of confused.
The answer to your question is right in this lecture. Maybe, okay, it's a good time to cover this here. So, suppose we have a large table in this file system, and when DBMS engine, query processing engine, requests a specific record, the DBMS engine should find out the location of that record, and it will look up its cache, in-memory cache. We call it buffer cache in DBMS. And if that page is not found, then we fetch the page from the file system, and then transmit the same page to this query processing engine. And for this, to fetch a new page, one of the oldest pages must be evicted from the cache. And at that point, if the evicted page is dirty, we cannot evict it. If the selected victim page is dirty, we cannot evict it. We should keep it in the buffer cache. Only if the page is clean, we can delete it from the page cache. So for that purpose, every page managed inside this buffer cache will have some additional metadata indicating whether this page has been updated or not.
스케줄 파일에서는 주기적으로 이렇게 모더링을 해서 다시 원 상태로 돌려야 되는 원 상태로 돌리는 과정이 필요하거든요. 그러면 그냥 애초에 처음 저장할 때 순서대로 저장하는 게 낫잖아요. 왜냐면 만약에 이걸 나중에 모더링을 할 때 말씀하신 대로 바이너리 소스 처음 이걸
No. So sequential files are created in a sequential fashion. Is that your question?
그게 아니라 그러니까 리모더링을 결국 분리가 해야 되는 거잖아요. 그러면
Only when some records are updated, only when records are deleted, there will be some free spaces intermittently, and they will be filled up by some incoming records. But usually, sequential files are used for read-intensive application. It's called warm semantics. Write once, read many. We write every data in just a single batch, and then we do not update it. We just keep reading it. Only for that use case, we use a sequential file. Does it make sense? Okay. Anyway, the sequential file format is the least important file format in this lecture. It seems it confused many of you guys. Let me check. I have only 5 minutes left. Right, let's finish up this multi-table clustering and column-oriented storage next time. And instead, let me explain these two more slides regarding the buffer manager. So for read operation, as I said, when we read a new page from Disqus, one of the old victim pages must be evicted. And for write operation, suppose a query insert a new record, then it will try to insert that record into a particular disk page, and that update will be buffered in this cache for a while. And we can keep that dirty page for very long time if we employ a technique called logging. Some DBMS do not use logging, very simple logging. If they employ very simple logging technique, then all those dirty pages must be immediately flushed to the file system when the transaction commits. Otherwise, we are going to lose that dirty data, right? So, when a new page is written, it is flushed to Disqus. And also, it is possible that this DB query processing engine decided to insert a new record R1 into page P10, let's say. And it is possible that page P10 is not cached in main memory. In that case, this write request will find out that the page 10 is not in the cache. Then it is going to bring the page 10 from Disqus, and then it will put this small record R1 into that page, and then flush it again. And while it is doing this again, any unused page will be removed from the cache. And when we use logging technique, like write-ahead logging, dirty data will be immediately written to log file, but database table file do not need to be immediately flushed. But still, periodically, those dirty pages need to be flushed to Disqus. And if we do not use this write-ahead logging these techniques, then as soon as a transaction commits a transaction, its dirty data should be immediately flushed to Disqus. And more details about this buffer manager and logging techniques will be explained in chapter 19. Any question about this buffer manager? If not, then I will see you next week.